We share.
Tutorial questions and answers.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others.
Please subscribe to our channel if you like our videos.
Before we continue the class, let's briefly take a look at something. Let's take a look at a problem like this, which is a simple example of a linear first order ordinary differential equation. And you can see from here that P here is a constant and Q is also a constant. At times, they may be function of x. But for this case, if you look at this one very well, you can see that a typical example is the y dx, the minus 2 y, then is equals to 4. Now, let's assume that we want to solve this problem. Normally, what we are supposed to do before is to look for what is called integrating factor, which is actually the same thing as integral exponential p dx. You know, in this case, we are having integral exponential p here is what? Is minus 2, then dx. Then, if you look at this now, this is actually the same thing as exponential minus 2x, because if you integrate minus 2 here, what we have is x, minus 2x, because there's x is super 0 here. So we have this. So this is the integrating factor. And what do we normally do before is that this method is simply the same thing as d dx of multiplied by integrating factor, then multiplied by the function we are looking for. You know, in this case, the solution to this particular problem is actually y of x. So exponential minus 2x, so multiply by the unknown function, which is y of x, then we close the bracket, then we say that this is the same thing as this 4 here multiplied by the integrating factor. So looking at this now, we are almost through. Let's us integrate both sides. So if you are to integrate both sides, you will see something like this. So this one will give me exponential minus 2x multiplied by y is equals to, if you integrate this one, this is something as 4 integral e minus 2x, then dx. So how do we integrate this one? This one will give me something like 4, then exponential minus 2x, then divided by minus 2, because if you are to differentiate the power of exponential here, then you divide it. So we have this. So this is the same thing as exponential minus 2xy is equals to, here we cancel here, we give me minus 2 exponential minus 2x. So what is the next thing now? Of course, then plus constant of integration. So the next thing is to divide both sides by this, because what we're looking for is actually y. So my y, which is the unknown function we're looking for, is not the same thing as minus 2 exponential minus 2x divided by exponential minus 2x. I'm dividing both sides by the coefficient of y here. So plus c divided by exponential minus 2x. So looking at this now, you see now that y of x, which is the solution of this first order linear ordinary differential equation, is now equals to, this one can cancel this to give me minus 2, are we together, then plus c, this one will come up, will give me exponential 2x. So that is not all. What if we need to find this constant of integration? Now let's consider this condition. Let's assume that y of 0 is actually 1. So what do we do now? Which means that we come back to the solution here. We assign this one to be 1. I'm talking about this one. So this will give me 1 is equals to minus 2 plus c exponential 2 multiplied by, what is the x now? X is 0. So 0. And anything over 0 is what? That's 1. That is 1 is equals to minus 2 plus c. So from here, we can see clearly that c is equals to 1 plus 2, that's what, 3. So let's return it back to the final solution here. So finally, we can now say that y of x is equals to minus 2 plus 3 exponential 2x. So this is the solution of this first order initial value problem. So this same problem here, We are going to use Laplace transform to solve it. Just like I've told you before, I said we can actually use Laplace transform to solve certain problems. We are going to limit ourselves to only linear. Laplace have some limitations when it comes to non-linear ordinary differential equations. So let's proceed.
So, like I've said earlier, that I will send a video to explain how to use Laplace transform to solve certain problems. We were unable to hold a class last week because of your MTS 201 test. I think you remember that. Okay, so let's go straight to the business of the day. So today we are going to use Laplace transform to solve first order ODE, second order, and then at the same time we are going to use this problem to solve a variable coefficient problem where we are going to obtain what is called Bessel function of order 0. So let's go straight to the point. Now, the first example on the board now, you can see now that we have dx dt minus 2x equals to 4. As you can see, the order here is what is 1. So this is actually first order, and it's actually, we can call it linear, and we call it initial value problem because we have the condition specified at a point. As you can see in equation 1, we have the problem subject to the boundary condition. So we're going to solve this one using Laplace transform. So, like I've explained before, I said once we know how to find Laplace transform of a function, we know how to find its inverse. That is all. So we only need to use the knowledge to solve problems. That's all. So let's solve this example number 1 now. The first step we're going to do is this. We are going to find the Laplace transform of both sides. So as you can see here, we put Laplace of the first derivative. Don't forget linear properties of Laplace transform. It means that this minus 2 can come outside because it's actually minus Laplace of 2x, but minus 2 can come outside. So we have minus 2, Laplace of x, and Laplace of 4. So what is Laplace transform of first derivative? You know that one. That is what we have on the board, this side that I'm trying to show you here. And what of Laplace transform of capital X, which is the unknown variable we are looking for? That is small x. What's the Laplace transform of 4? That is 4 over x. So that's all. Now the next thing is for us to group. Now look at this. Look at the condition. The condition we have at the problem is x of 0 is 1, which is the same thing as small x of 0 is 1. So we are going to replace this one with x of 0 is 1. So this one I'm trying to circle here. So by the time you change this one to 1, so you now have x of x, then minus 1, then minus 2x of x. I've changed this x to x of x so that I can say clearly that it's actually depending on x for school. So it's equals to 4 over x. So what's the next thing now? Minus 1 will go to the other side. So if that is the case, then 2x of x, we can factorize it from this one. So you now have x minus 2 into bracket x of x. So that will give us 4 over x plus 1 over 1. X multiplied by x minus 2. That is how we obtain this equation 2. This is what I was saying. See, everything here will come here. We come to the other side. And here it happens to be a numerator before, then here it will become a denominator. So that is what we have now, equation 2. Now, what is the next thing we need to do now is that we need to find Laplace inverse of both sides. So Laplace inverse of this, then Laplace inverse of this. Now look at this. Look at how I put it. If you open your lecture note, page 24, I said the next thing is to find the Laplace inverse of both sides. So we have inverse A, we have inverse A. Now look at this. Now can you now see why I was saying the other time that there is no way you can use the Laplace transform without the knowledge of partial fraction? Because here, I have 4 plus x over x into bracket x minus 2 is a fraction. But I want to break it down to a simple fractions. So what am I going to do now is this. I bring it this back to focus on only this. So, and look at it, x here, that will be a over x, then b over x minus. Remember the 6 rules I explained in my last video. Okay, so we have a over x, then b over. Now the next thing we're going to do, here, we are only using the knowledge of partial fraction now, nothing else. We are outside the scope of Laplace transform this time around. So take note of that. So I would advise you, please, if you can lay your hand on any of your textbook on partial fraction, please do revision before exam, okay? So now what's the next thing? Now we divide both sides by the denominator of what we have at our left hand side. So when you multiply both sides by this one, that thing we cancel this, we struck it out. So what we now remain is 4 plus x is equals to, now everything we have here, let's put it down beside the first term here. So you see that x will cancel x. So what will remain is a into bracket x minus 2 plus, if you put everything, you put it down here, x minus 2 will cancel x minus 2, then what will remain is b multiplied by x. That is our equation 4. Okay, now we need to find a and b. So what do we need? Firstly, if you look at x minus 2 is equals to 0, x minus 2, then definitely it means that x is actually 2. So if x minus 2 is 0, then a will vanish. Then what will remain is what is b. So let's now set x equals to 2. Don't forget, how do I obtain x equals to 2? From here, because I want to set this coefficient to 0. So if x minus 2 is equals to 0, is 0 times a will give us 0. Then that is how I know that from that x is equals to what? To 2. So let's put it down in equation 4. So put 2 here, that will be 4 plus 2, 6. Put 2 here, it will give us 0. Then put 2 here, that will be 2b. So from here, you can see that b is 3. Now, what's the next thing again? We need to find our a. We need to find a. So here now, there's nothing we can actually set to 0 directly like that, because what we are looking for is a. So if you set, or perhaps you can actually set this x to be 0. Because if this x is 0 here, is 0 we cancel b, then you have a into brackets is 0 minus, that will be minus 2a. And this one too is 0, then you have 4. You see that at the end of the day, you have your a to be minus 2. But in this lecture now, I actually use x equals to 1. So when x is 1, 4 plus 1, that is 5. 1 minus 2, that is minus 1. Then you have minus 8. That's how we obtain this. Then b times 1, that is actually b. So what is the next thing now? Let's return b equals to 3 here. So we have 5 into bracket equals to a minus 1 plus 3. So if this one should go to the other side, then that will give us 5 minus 3, that is 2. Then a times minus a, that is given. So from here, you can see that a is 2. Then let's go back to the fraction now. This big fraction is now equals to minus 2 over x plus 3 divided by x minus 2. So let's go back to the problem, from here, which is our equation 3. So Laplace inverse of x for school, that will give us x of t. The Laplace inverse of this fraction now will give us minus 2 over x plus 3 divided by x minus 2. So what is the Laplace inverse of minus 2 over x and Laplace inverse of 3 divided by x minus 2? So from here, you can see that this one here is the same thing as minus 2. Remember, Laplace transform of 1. Okay, that's 1 over x. So the Laplace inverse of minus 2 over x is the same thing as minus 2. So what about this one too? This one, remember, this is the same thing as exponential 2t. Then you have minus 2 plus 3 exponential 2t. So you now see that the solution we obtain here is the same thing with the solution we obtained in my first exam, where I actually solved the same method using integration directly, using integrating factor, you remember. So that is how to solve first order ODE using Laplace transform. Now, if you open your lecture note to page 25, you will see where I said you should show clearly how to solve the following. It's actually 2 questions, how to solve the 2 problems using Laplace transform. So without wasting our time, let's go to second order. Now, we are still on page 25. So we have this problem now. This is the second order, because you can see that the highest derivative is what is 2. So, and at the same time, it is actually non-homogeneous, because at the other side, you can see exponential minus t sine t. And it's actually linear, because all the coefficients of the derivative here, they are constants. Here we have 1, here we have 2, here we have 5. So it's actually a constant coefficient. So if you are to describe this problem now, how will you describe it? Okay, no, that's not all. Let's take a look at the condition 2. The 2 conditions, we have them at 0. Look at this, x of 0, x prime of 0. So how do you describe this problem now? This is actually second order, ordinary differential equation, non-homogeneous, then initial value problems. So I call it initial value problem because we have the 2 conditions specified at 0. So let's solve this problem now using Laplace transform. Just like I've explained before, find the Laplace transform of both sides. So Laplace transform of second derivative plus 2 times Laplace transform of first derivative plus 5 times Laplace transform of x, then Laplace transform of exponential minus t sine t. So let's start from this. Laplace of second derivative will give us this. I think you remember that. Laplace of first derivative will give us this. Then Laplace of x will give us x. Now, what about this? We are going to use translational principle. You remember? So, because from here, if you find Laplace inverse of sine t, that is 1 over x squared plus 1. Then Laplace inverse of exponential minus t sine t will now give us 1 over x plus 1 squared plus 1. So, return everything back to the problem, you have this. You know, here, x plus 1 square is same thing as if you expand x plus 1 square plus 1. This is what you have. You have x squared plus 2x plus 2. So before we proceed, let's try to introduce the conditions. The first condition is that x of 0 is 0. So let's come back here. This is x of 0. We change this one to 0. And the next second condition is x prime of 0. That is the derivative of x with respect to x at x equals 0 is what? Is 1. So wherever you see x prime of 0, which is, this is 1, we equate this one to 1. So look at it, x squared of x, we still have this one. This one here, we change to 0. X of 0, we change to 0. So you have 0 here. Then this one will give us minus 1. This one will give us 2x of x. And this one will give us minus 2 of 0. And this one will give us 5 plus x, 5 times x. Then you have this. So what is next now? We group the factors. We group them together. So as you can see here, we still have them here. But minus 1 will go to the other side. There's no way. So that everything we have here will be depending on x for xylophone. So we have x here. So by the time you factorize, you have x squared plus 2x, then plus 5 multiplied by x for xylophone. Then you have everything here, then plus 1 over 1. So we have this. So by the time you find the LCM, you find the LCM of these sides. No, even in my lecture, I still don't find the LCM. I just put it like this. Okay, no, the LCM of this and this will give us this. And likewise, this one here, you divide both sides by x squared plus 2x plus 5. Then you can see that's how we obtain this. Now, you can ask, remember when I said we're going to use Laplace transform to change from t domain to x domain. I said when we get to x domain, we're going to use the knowledge of partial fraction. Do you remember? That is where we are. Because look at this fraction, it looks big. It looks big, but we are not interested in that. We want to break this one down because as I'm looking at this one directly, you may find it difficult to know the Laplace inverse. And that's where we're going to obtain our solution. So there's no way, no, I would advise you, please. You can check my lecture note again. That should be around page 15, 16, where I actually explain the rules. So when you get there, not page 16, that is actually page 18. Okay, page 19. Please, I would advise you to pay attention to those. I said rules of partial fraction. So we actually have 6 rules there. So please pay attention to look at that because there's no way you will use partial fraction Laplace to solve the problem, and you will need the knowledge. So let's deal with this now. Inverse of both sides first. So we have inverse of this. It's not big. Let's take a look at it now. Everything that we have here, we come down here. Now we want to use partial fraction. How do we break this one down? This is quadratic. So the numerator will be linear. Are we together? Let's say that this one is x3. Then the numerator will be x squared. Of course, if the denominator is x3, that means that you need 3 constants. That will now give us ax squared plus bx plus c. But in this case, this is actually quadratic. So what we need is ax plus b. Then divided by the first one, then plus. The second one is also quadratic. So we need 2 constants and linear. That will give us cx plus d. So that is the first rule. And if you can see in your lecture note, that is actually, if you look at page 19, rule number 5. That is actually, no, rule number 6. That is what they call it, repeated quadratic factors. So that is actually what we are using here. So if you look at that now, you have this expression. Now, what is the next thing? You multiply both sides by the denominator. So this is the denominator. By the time you multiply both sides by the denominator, it will cancel this side. Then what will remain is x squared plus 2x plus 3. That's how we are obtaining this. But by the time you put everything down here, it will cancel this. Then you have this. By the time you put everything here beside ax plus b, this one will cancel this. It will cancel this. So what will now remain is ax plus b multiplied by x squared plus 2x plus 5. You multiply this one again by everything here. So this one will cancel this. So what will remain is cx plus z multiplied by x squared plus 2x plus 2. So we have that now. So what's the next thing now? As you can see, if you can see in this lecture note, what I'm actually trying to do is to expand. That I can actually expand this. Do you get the point? Let me explain it to you again. Look at this now. We have, if you expand this time this, this time this, this time this. If you expand it, you will have the highest part to be x to the power 3. Then by the time you expand, Then you collect all the factors. Like the one with S3, you group them together. The one with X squared, you group them together. The one with X, you group them together. The one with another constant, you group them together. So you now compare the coefficients now. That means that this one here will be equals to X squared. Are we together? And this one here will be equals to 2. And everything here will be equals to what? To 2. And then, okay, you know, you don't have x is over 3 here. Do you notice that? There's nothing like x is over 3 here. That is why we equate this one to 0. And for x squared, you equate to 1 because x squared is equals to this. We are comparing the coefficients. And for this one too, you compare with this. For 3, you compare with it. That is how we obtain these 4 equations in page 27. So our advice, if you have calculator or you know how to solve this one simultaneously. What you have is 0, 1 over 3, 0, and 2 over 3. Now let's return it back to the problem. So you can say that Laplace inverse of this problem is the same thing as Laplace inverse of 1 over 3. You know this is a x plus b. That's 1 over 3 divided by c. Then plus 2 over 3, then divided by this. So you now find the inverse of this. 1 over 3 will come outside, and then from here, look at what I've done here. This one here, I can actually express this one in terms of square. Remember, I was trying to jump during one of our classes. Can you see now here? Because what I'm trying to do here is this. This is x squared. This is plus 2x, right? And to make this one perfect square, if I break this one to 1 plus 1, because I know that 1 squared will make the remaining to be a perfect square. So this one to 2 over 3 will come outside. I will use the same knowledge here to make this one a perfect square. So that is how we obtain this. So from here, we can answer 1 over 3. Here, this is exponential minus t sine t. Don't forget, translational and shifting principle. And for the second one too, 2 over 3, the Laplace inverse of this one will give us this. So that is how we obtain the solution. Don't forget that we actually use this one to solve initial value problem, but second order. See, it is initial value problem because you have a 0 here. Here, you have a 0 here. So this is actually second order initial value problem. Now let's go and use Laplace to solve boundary value problem now. Look at this question on exercise 2, page 27. Look at this one. This is second order, right? Second order, but this is boundary value because we have 2 conditions and one condition is specified at 0 while the second one is specified at pi over 2. So let's use the Laplace to solve this problem now. Now note that for us to solve this one, we need y prime of 0. Do you remember that? It's very simple. Let me explain the secret to you. By the time you find Laplace inverse of second derivative, you are going to have y prime of 0. Do you remember? Of course. But if you look at the condition, we don't have something like that. That is the reason why we need to assume, we need to set y prime of 0 to be a constant. That is just it. So take note of whenever you are using Laplace to solve boundary value problem, one condition will be missing. And the best thing for you to do is to actually assign a constant to that missing condition. So let's proceed now. Laplace inverse of both sides. Laplace of second derivative will give me 1, 2, 3, the first 3. Laplace of y will give me y, that's 9 times y. Then Laplace of cos 2t will give me x over x squared plus 4. Now what's the next thing now? Let me substitute. This is y of 0. Y of 0 is 1. Then what is y prime of 0? That is c, the one we assumed. So let's put this one here now. So what's the next thing now? Let's group the factors together. If you group, c will go to the other side. X multiplied by 1. We also go to the other side. So here, what I will now have is x squared y, then plus 9y. So I can factorize to have y. So that will give me x squared plus 9. Then it's equals to. Now everything we have at this side, we need to use the knowledge of LCM to group it together to give us one fraction. So this will now give me, if we find the LCM of this is what we are going to obtain. So what is next thing now is that we can actually break this down, this fraction here, to give me x over x squared plus 9, which is this one, plus c over x squared plus 9, which is this one, equals to 2. So you can see in your lecture note I said it's an assignment that you should go and use partial fraction to show that this one here is equals to this. It's very simple, just like I've been explaining before. So if you do that, that is what you obtain. So let's return it back to the problem. So we have this. We should return it back. So we have this. So the next thing is for us to group it together. It's very simple. See, I just only group the first, second, and the last. Then you group others too. Then you find inverse of both sides. So by the time you find inverse of both sides, so you have this. So you have this expression. But remember, we are still having constant C here. And we need to find C. So how do we find C now? We are going to use the missing condition, which is y into bracket pi over 2 is equal to -1. It's very simple. See, the condition is at y, but at pi over 2. And by the time you find inverse of both sides, you already have y here now. So we are going to use this expression to find C. So what do? You set this one to be -1. Then t, you set t to pi over 2. So with that, you'll be able to find C. Because by the time this one is -1, and wherever you see t, you set this to pi over 2, then you can find your C to be 12 over 5. So you return it back to the problem. So that is how to use the Laplace transform to solve boundary value problem. It's very simple. The only thing is that there will be a missing condition. That is just it. Don't forget, if you are solving second order, you need 2 conditions. If you are solving third order, you need 3 conditions. So since it's a boundary value problem, one of the conditions will be specified at the other point. So you just assume this to be a constant. That is just the secret, and you are good to go. So before we proceed, let's just take a look at certain things we call gamma function. We have gamma function, which is what you can see on the board. Is 0 to infinity un-1 exponential minus u du. That is the expression for gamma function. And also, we also have what is called Bessel function of order n. You see that one on page 29. So all this one, just take note of it, that we have something called special functions. Okay. Now, let's take a look at this. If f of t is j naught a of t, if we find Laplace of both sides of this, what we have is 1 over x squared plus a squared, then square root. Take note of that. And let's take a look at if it's of order n. That is, if f of t is j and a of t, if you find Laplace inverse of both sides, what we have is this expression. And you will see that when n is 0, you will still get this expression back. Because when n is 0, n raised to the power 0 is what is 1. And a raised to the power 0 is what is 1. Then you multiply this, you still have this expression back. So that is it. Now, let's take a look at this. Look at this problem on the board. Now I said variable coefficients. Don't forget why we call it variable coefficients. So now we are asked to solve the following problem now. So this is boundary value. So that we have the condition at 0 and pi over 2. We have the 0 and minus at 0. So this one is initial value. Question number 2 is initial value, while question number 1 is actually boundary value problem. So let's solve this variable coefficients now. On the board, you see the problem. We have t multiplying the second derivative. Do you remember? Okay, look at that now. If t is multiplying, t is the independent variable here now. Y is depending on what? On t. So we have this expression subject to this condition. So what is the next thing now? Let's start. You find Laplace inverse of both sides. That's how we obtain this. Laplace of this t raised to the power 1. Okay. Now, secret number 1. Do you remember when we were dealing with that is t n f of t? Do you remember? And if you check the lecture, I said it's more or less as if -1 raised to the power n, then dx(n), then f of x. That's what we're going to use here now. Because this is t raised to the power 1. If we know Laplace of second derivative, then we are going to differentiate it once, because we have t raised to the power 1. And if we have t squared y prime prime, that means that we're going to differentiate the Laplacian of second derivative twice. Then you multiply by this formula. You can open your lecture notes. I think we have that expression somewhere. That is page 15. Multiplication by powers of t. So let's proceed now. So what's the next thing now? Laplace of first derivative is this. Then you differentiate this once. By the time you differentiate, you have this. So you return everything back. By the time you return everything back, then you group Then here you can see that here we're having integrating, you need to integrate both sides. So by the time you integrate both sides, you have this expression. It's very simple. Ln of y then plus, because by the time you arrange this one, you can arrange this one to give us this. So you integrate both sides, then you have a constant. By the time you integrate once, you have a constant. So that's why we have C here. And by the time you find inverse of both sides, can you now say where the z function of order 0 will come out now? So that's how to do that.
We share.
Tutorial questions and answers.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others.
Please subscribe to our channel if you like our videos.